Friends, welcome to the next session of the subject Engineering Mathematics. Now in this session, we discuss classroom workbook questions based on eigenvalues and eigenvectors. Just let us start the session with question number 52. Just go through your handout. Let us go through question number 52. So if A equal to 1 0 0 0 minus 1 plus I root 3 by 2 0 0 0 minus 1 minus I root 3 by 2. Then what is the trace of A power 102? This is the question. Trace of A power 102. Now this is a diagonal matrix. Upper triangular, lower triangular. If it is either upper triangular or lower triangular matrix, my eigenvalues are diagonal elements, right? You can see now this is my diagonal elements. Now all elements above diagonal are 0. So this is a lower triangular matrix. Or all elements below diagonal are 0. This is an upper triangular matrix. If it is either LT or lower upper triangular, its eigenvalues are diagonal elements. So lambda 1 is 1, lambda 2 is minus 1 plus I root 3 divided by 2, comma lambda 3 equal to minus 1 minus I root 3 divided by 2. Now these three are eigenvalues of A. Now I want trace of this. Now these are eigenvalues of A. To find this trace of A power 102, let us find the eigenvalues of A power 102. These are eigenvalues of A. Therefore, eigenvalues of A power 102 are 1 power 102, comma minus 1 plus I root 3 by 2 whole power 102, comma minus 1 minus I root 3 divided by 2 whole power 102. Now these are eigenvalues of A power 102. Therefore, trace of A power 102. Trace of this matrix is sum of its eigenvalues. These three are eigenvalues of A power 102. Add all this. 1 power 102 is 1. So 1 plus minus 1 plus I root 3 by 2 whole power 102 plus minus 1 minus I root 3 by 2 whole power 102. Now the difficulty at this moment is how to find minus 1 plus I root 3 by 2 whole power 1 by 2 and minus 1 minus I root 3 by 2 whole power 1 by 2. They are complex conjugates. So simplifying this is a little bit complicated. Now let me explain what are those values. Basically these three numbers 1, minus 1 plus I root 3 by 2, comma minus 1 minus I root 3 by 2. These three numbers are roots of the equation x cube equal to 1. Roots of x cube equal to 1. So this is a third degree equation. When you solve this equation, you will get three roots. These are nothing but these three roots. Now let us see, basically this is roots of x cube equal to 1. This is x cube minus 1 cube equal to 0. This implies this is in the form a cube minus b cube. This is a minus b into a square plus ab plus b square equal to 0. Now when you simplify this equation, you will get x value 1. When you find the roots of this equation, quadratic equation, one root you get it as minus 1 plus I root 3 by 2. Another one is minus 1 minus I root 3 by 2. This is simple to verify. Therefore, in this context, this number, this number, this number, all the three numbers are roots of the equation x cube equal to 1. Even you can cross check this. This is a third degree equation. So this is in the form x cube minus 1 cube equal to 0. The factorization is x minus 1 into x square plus x plus 1 equal to 0. Now when you simplify this, you will get 1 root 1. This one is nothing but this one. Now this is a second degree equation. When you try to find its roots, you will get these two complex numbers as roots. Therefore, this is nothing but cube root of 1. So x cube equal to 1 means what? X equal to 1 power 1 by 3. Therefore, these values are nothing but this value, this value, this value are nothing but cube roots of 1. Cube roots of 1. Therefore, at this moment, I can write this expression, I can write it as 1 plus, this is nothing but cube root of 1. So, we can write it as 1 power 1 power 1 by 3 whole power 102. Even this is also cube root of 1. So, 1 power 1 by 3 whole power 102. So, this is 1 power. So, 102 by 33, 34, 34, 1 power 34, 1, 1. So, therefore, this is 3. Note this point. This is one of the extraordinary gate question. Is this question clear? Right. Next question. Question number 53. For the matrix A, satisfying the equation given below, the eigenvalues are. So in this question, the entire matrix is, the whole matrix is not given, but instead of giving the matrix, they gave like this. The matrix is like this: A into 1, 2, 3, 7, 8, 9, 4, 5, 6 equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the equation given. We need to find eigenvalues of A. Eigenvalues of A. We need to find out this. So here matrix is not given directly. Indirectly it was given. When you transform this, one way is you can find the matrix A. This can be done like this. Assume that this is matrix X. A into X equal to B. This implies AX into X inverse equal to B into X inverse. This implies A equal to B into X inverse. So this is A is possible by multiplying this B with X inverse. But if you want to find the inverse of this matrix, its det should not be 0. But interestingly, this is X, this matrix is X, and this is B. Now, when you calculate the determinant of this matrix B, this matrix X, its det is 0. Because of the reason this is nothing but 1 plus, this 4 is nothing but 1 plus 7 by 2. 5 is 2 plus 8 by 2. This 6 is 3 plus 9 by 2. That means R3 is linearly depending on R1 as well as R2. 1 plus 7, 8, 8 by 2, 4. 5 is 2 plus 8, 10 by 2. 3 plus 9, 12, 12 by 2, 6. Therefore, here R3 equal to half of R1 plus R2. This is nothing but linearly dependence relationship among rows. Whenever there is a linearly dependence relation among rows, det is 0. When det is 0, inverse is not possible. So, X inverse does not exist. Therefore, by this way, you cannot get the matrix B, the matrix A. Now, let us see how to get eigenvalues of A. One way is this. Here it is given as A into X equal to B. Apply det value on both sides. Det of AX equal to det B. This implies this is det A times det X equal to det B. Now when you observe this matrix and this matrix, what is the difference? Here first row is 1, 2, 3, this is 1, 2, 3. Row 1 is same. Here this second row becomes third row and this second row becomes third row. Therefore, what is the difference between this and this? Exchange of second and third rows. Therefore, if the det of this matrix is K, the determinant of this matrix is minus K. When two rows are exchanged exactly one time, that is odd number of times, that is affected by minus sign. That is affected by minus sign. But therefore, in this case, you can write like this: det A into this det of X. You can write it as a minus of det B equal to det B. So det B you can cancel out. Det A equal to minus 1. But det A is nothing but product of eigenvalues. This is 3 by 3. This is 3 by 3. Therefore, this is a matrix of size 3 by 3. Therefore, det is product of 3 eigenvalues. Lambda 1 into lambda 2 into lambda 3. This is minus 1. Now, when you verify options, let us multiply first option values. 1 into minus j into j. That is not 1. So, option A is eliminated. Option B, 1 into 0, not minus 1. Eliminate that. Option D, 1 into 0 into 0. That is wrong. But when you multiply all values in option C, you get minus 1. So, C is expected answer. But there is some wrong evaluation in this derivation. Can you guess that? There is wrong evaluation in this derivation. There is some big mistake at this moment. How I will get this from this? By cancelling B on both sides. Here operation is dot. How can you cancel 0 on both sides when it is multiplied with a dot? So therefore here det B is 0. Its det is 0. Its det is 0. Therefore you cannot cancel out on both sides. Therefore this is a wrong approach. This is a wrong approach. Now let us see how to, generally students may think in this direction also, but this you can cancel a number which repeats on both sides if the operation is dot only when it is a non-zero number, right? Now let us see how to handle this. The difference between this and this is almost same by exchanging second and third row. Suppose if this and this both are same, let me write this: AX equal to B. Suppose if this and this both are same, then this could be identity matrix. If this matrix and this matrix both are same, definitely this must be identity. But the difference between these two is second and third row have been exchanged. Therefore, this matrix A is nothing but identity matrix of size 3 by 3 by exchanging second row with the third row. Therefore, A is a 3 by 3 identity matrix with exchanging second row and third row. Therefore, det of I equal to minus 1. Det of I3 is 1, but two rows have been exchanged. Therefore, it is minus 1. Now, it is lambda 1 into lambda 2 into lambda 3 equal to minus 1. Therefore, option C is right answer. Even you can cross check this. You replace A by 3 by 3 identity matrix with exchange of second and third rows. So, third row is this and second row is this. So this is I3, 3 by 3 identity matrix by exchanging second row with third row. Multiply this with this, you will get this. Normal evaluation. Therefore, this A is nothing but a 3 by 3 identity matrix by exchanging second and third rows. Therefore, A is I3 by exchanging second and third rows. So det A becomes minus 1. Because det of I3 is 1, but two rows have been exchanged, that is affected by negative sign. But that is product of eigenvalues. Lambda 1 into lambda 2 into lambda 3 equal to minus 1. Therefore, only when you multiply values in option C, you will get minus 1. So, option C is right answer. This is one of the best question in GATE 2014. Is this clear? Right. Next we proceed to question number 54. Consider the matrix 0, minus 1, 2, 1, 0, 3, minus 2, minus 3, 0. Which of the following is incorrect? One of its eigenvalues is 0. It has two purely imaginary eigenvalues. It has a non-zero eigenvalue. The sum of its eigenvalues is 0. Look at this question. This is a skew symmetric matrix. This is a skew symmetric matrix. Size is odd. Assume that this matrix is A. So when A is a skew symmetric matrix of odd size, its det is 0. And of course, this is a real skew symmetric matrix. All eigenvalues are either 0 or purely imaginary. Either 0 or purely imaginary. Now look at this. Its det is 0. So at least one eigenvalue will be 0. Now when you look at this is a 2 by 2 submatrix 0, minus 1, 1, 0 whose det is not equal to 0. So there is a 2 by 2 submatrix whose det is not equal to 0. So therefore rank of this matrix is 2. Since its rank is 2, it has 2 eigenvalues. But they are purely imaginary eigenvalues. There is a twist in this question. Generally people may think in this direction also. Since the rank is 2, it has 2 non-zero eigenvalues. In option, it has a non-zero. In option C, it is given that it has a non-zero eigenvalue. It is meant for non-zero real eigenvalue, because you cannot compare complex eigenvalues with 0, right? See, option A is right option. Actually, right statement, not right option, right statement. It is given that which of the following is incorrect. In first option, one statement is given, that is the right statement, because its det value is 0. It is a skew symmetric matrix of odd size. Its det is 0. So when det is 0, at least one eigenvalue will be 0. So one of its eigenvalue is 0. So that is a right statement. Next, since its rank is 2, you will get 2 non-zero eigenvalues basically, but they meant for purely imaginary, because we know that all eigenvalues of a real skew symmetric matrix are either 0 or purely imaginary. Since its rank is 2, it has the 2 purely imaginary eigenvalues. That is also right statement. Option D, the sum of its eigenvalues is 0. Trace of skew symmetric matrix is always 0. Sum of eigenvalues means it is a trace. As we mentioned in the last sessions, trace of a skew symmetric matrix is 0. So therefore, option A, option B and D, they are right statements. But we want incorrect statement. Therefore, the incorrect statement is it has a non-zero eigenvalue. It is meant for non-zero real eigenvalue, because there is no comparison among complex numbers with 0. So complex numbers cannot be compared with 0. That is the key point. So option C is a required answer in this question. That is the incorrect statement. Please write this point. Here A is a real skew symmetric matrix of odd size. Here A is a real skew symmetric matrix of odd size. Here A is a real skew symmetric matrix of odd size. Therefore, det A equal to 0 implies one of its eigenvalues is 0. Implies one of its eigenvalues is 0. Since rank of A equal to 2 implies A has 2 purely imaginary eigenvalues. Since rank of A equal to 2 implies A has two purely imaginary eigenvalues. Next point, trace of A equal to 0. Right? Therefore, C is incorrect statement. That means C is required answer in this case. Now let us move to question number 55. Very, very worthwhile question. Question number 55. Let A equal to Aij. Elements are denoted by Aij. It is a 10 cross 10 matrix such that Aij equal to 1 for all I not equal to j, alpha plus 1 if I equal to j, where alpha is greater than 0. Let lambda and mu be the largest and smallest eigenvalues of A respectively. Lambda is the largest eigenvalue, mu is smallest eigenvalue of this matrix. And it is given that lambda plus mu equal to 24. So in that case, what is the value of lambda? This is my question. See, here my matrix is size is 10 by 10. So in a 10 by 10, 100 elements will be there. But interestingly, when I equal to j, they refer to diagonal elements. So all diagonal elements are alpha plus 1, where alpha is greater than 0. I equal to j means they refer to diagonal elements. So all diagonal elements are alpha plus 1, where alpha is greater than 0, fixed number. But I not equal to j means non-diagonal elements. So non-diagonal elements are restricted to 1. So you will get 10 by 10 matrix. All diagonal elements are alpha plus 1 and rest of the elements are 1. So like this, a 10 by 10 matrix is given. So it is given that lambda is the largest eigenvalue of such matrix and mu is the smallest eigenvalue of that matrix. And moreover, lambda plus mu equal to 24. In that case, what is the value of lambda? Now the practical issue in this case is its dimension, right? If it is 2 by 2 or 3 by 3 or somehow 4 by 4, we can manage. Of course, it takes some time, but we can manage. But if it is a 10 by 10, then finding largest and smallest eigenvalues may be tough. Here size is very complicated, so definitely there will be some flexibility in terms of elements of that matrix. This is the flexibility. So non-diagonal elements are 1, diagonal elements are restricted to alpha plus 1. Now let us minimize this question to the smaller versions without changing the meaning of the question. Let us see. Suppose I am taking with alpha equal to, for example, 3. Suppose I am taking with 2 by 2 matrix, for example, 2 by 2 matrix. Now in this case, my matrix is this, A equal to, so actually this is my matrix, alpha plus 1, alpha plus 1, 1, 1. So here I am minimizing this problem to 2 by 2 size. My diagonal elements are alpha plus 1, rest of the elements are 1. So here assume that alpha equal to 3 because alpha is any number which is greater than 0. You can take any number. So alpha value I am starting with 3. So this is 4, 1, 1, 4. Now therefore, what are the eigenvalues of this matrix? The eigenvalues of this matrix are 5 because sum is 5. What is the trace of this matrix? 8. One eigenvalue is 5. So second eigenvalue is 3. So this is smallest, largest and this is smallest eigenvalue. So smallest eigenvalue is this. And largest is this. Therefore, what is this? Let me explain this in terms of alpha. So what is my largest eigenvalue? 5. So in this case, lambda is 5. Lambda represents largest eigenvalue. So this is 5. So this I can write it as 3 plus 2. 3 plus 2. And this is alpha value. And this represents size of a matrix. Here I started with the size 2. And smallest eigenvalue is mu and that is 3. And this 3 is nothing but alpha value. This 3 is nothing but alpha. This is the simple logic. Even you can manipulate with the different examples also, you can get the result easily. Therefore, in this case, what is my largest eigenvalue? Alpha plus size. Smallest eigenvalue is alpha. See, what is the practical issue in this question? It's the dimension. You can't find, it is not so simple to get the eigenvalues of 10 by 10 matrix. And in particular, it is very difficult to find largest and smallest eigenvalues. Therefore, what we are doing is, we are minimizing the size of the question without changing meaning of the question. So here I started with a 2 by 2 matrix. My diagonal elements are alpha plus 1. Non-diagonal elements are 1. So alpha plus 1, non-diagonals are 1. Start with 2 by 2. Size, alpha is 3, for example. Then my matrix is reduced to 4, 1, 1, 4. So column sum is 5. So therefore 5 is one eigenvalue. Trace is 8. So second eigenvalue is 3. Because sum of eigenvalues must be trace. 5 plus 3 equal to 4 plus 4. So this is the largest eigenvalue, this is smallest. So here in this context, lambda is largest and mu is smallest. Now this 5 I can represent like 3 plus 2 in terms of alpha. This is 3. So 3 plus 3 is alpha. This 2 is nothing but size. So largest eigenvalue is alpha plus size. Smallest eigenvalue is alpha. Even you can change different numbers, you can easily predict this. Therefore, in this context, what is the largest eigenvalue? Alpha plus size of this matrix is 10. Smallest eigenvalue mu is alpha. It is given that lambda plus mu equal to 24. So this is alpha plus 10 plus alpha equal to 24. This implies 2 alpha equal to 14. This implies alpha equal to 7. So this is my required answer. If you have any queries, still if you have some queries, just manipulate with a 3 by 3 example or 2 by 2 by taking different alpha values. Then you can easily get the answer. If you have some more, if it is not clear till now, just take different values. You take alpha equal to, for example, 4. And matrix is size 2 by 2. Then my matrix is alpha plus 1. So this is 5. And this is anyhow 1. This is 1, 5. So largest eigenvalue is 6. Smallest eigenvalue is 4. 5 plus 1, 6. 1 plus 5 is 6. This is 6. So sum is common. Largest eigenvalue 6. Trace is 10. Already 6 is covered. So second eigenvalue must be 4. Now this is what? 4 plus 2. And this is 4 only. So largest eigenvalue is alpha plus 2. Smallest eigenvalue is alpha. Like this, you can go for 3 by 3 also. You take alpha equal to, for example, minus 2. Take some 3 by 3 matrix. Find its eigenvalues. Express largest and smallest eigenvalues in terms of the variable alpha. Then, when you generalize this, largest eigenvalue will be alpha plus 10 because 10 is the size of this matrix. Smallest eigenvalue is alpha. So proceed this, you will get alpha equal to 7. This is one of the extraordinary gate question. Extraordinary gate question. Always prefer lower dimension matrices. If the question becomes so complicated, minimize that size of the question without changing the meaning of the question. Then you will get some clarification. Instead of leaving the question completely, if you minimize the size of the question, then you will understand some points easily. You will get some clarifications. I think this is very clear. Now let us move to question number 56. What is question number 56? For the matrix 4, 3, 3, 4, if 1, 1 is an eigenvector, then the corresponding eigenvalue is, matrix is given, eigenvector is given, you need to find lambda. Just apply the definition of eigenvector. A into x equal to lambda into x. A is this matrix 4, 3, 3, 4 into x is this eigenvector 1, 1 equal to lambda into 1, 1. Just you can expand either first row or second row. You will get the same value. Expand first row 4 into 1 plus 3 into 1. 4 plus 3 equal to lambda. Therefore, the eigenvalue is lambda equal to 7. Next we move to question number 57. One of the eigenvectors of the matrix minus 5 2 minus 9 6 is. So they were asking one of its eigenvectors. Options are given. Interestingly, here the eigenvalue is not mentioned. So that is our responsibility. So we need to find lambda 1 and lambda 2. So first you find eigenvector with respect to lambda 1 or lambda 2. If it is there in options, opt it. If it is not there directly, instead of that, if its non-zero multiples are available, then also you can opt it, because non-zero multiples of eigenvectors will be acting as again eigenvectors, right? Now it is our job to find eigenvalues at first, because for eigenvector, eigenvalue is required. Now add these two elements, minus 5 plus 2, minus 3, minus 9 plus 6, minus 3. So sum of R1, sum of R2, minus 3. So one eigenvalue is minus 3. The trace is 1. Already minus 3 is covered. So second eigenvalue is 4. Minus 5 plus 6, 1. Minus 3 plus 4 is 1. Now these are my eigenvalues. Now let us try to find eigenvector with respect to lambda 1 first. So there is no procedure. You can find eigenvector with respect to 4 also. Anyhow, I got first eigenvalue minus 3. So I am proceeding to find eigenvector with respect to minus 3. Let us apply shortcut. The shortcut to find the eigenvector of a 2 by 2 matrix is this, a minus lambda 2i. So what I am doing is, I am trying to find eigenvector of this matrix. Assume that this is A. I am trying to find eigenvector of this matrix A with respect to this eigenvalue lambda 1. For that, I need to find a minus lambda 2i. If it contains non-zero columns, then they act as eigenvectors with respect to minus 3. If those eigenvectors are available in the options, I can opt it. Now let us see. This is a minus lambda 2 is 4i. So subtract 4 from diagonal elements. So minus 5 minus 4 minus 9. 6 minus 4 2. And keep the non-diagonal as it is. Minus 9 2. Now in this case, this is a non-zero column. Of course, this is also non-zero column. But that means eigenvectors are this. Minus 9 or 2 2. Now let us see whether these are available in options. Exactly. In option D, we have 1 1. A value, B value same. If this is an eigenvector, then minus 1 by 9 into minus 9 minus 9. This will be an eigenvector. This is nothing but 1 1. Just A value, B value same. A value, B value same. A value, B value same. Therefore, option D is right answer. Option D is right answer. Suppose if its multiples are not, non-zero multiples are not there in the option, then they are expecting eigenvector with respect to 4. Not this. the value of k such that 1, 2, 3 is an eigenvector of the matrix 4, 1, 2, k 2, 1, 14 minus 4, 10 is blank. So whole matrix is given but one element is missing. So for this matrix, if this is an eigenvector, then what is the value of k? Here lambda is missing. So matrix is not given but not completely. One value is missing that he named as k. Whole matrix is given except one entry, that is k. If this is an eigenvector of this matrix, then what is the value of k? So our responsibility in this problem is we need to find lambda. Once you get lambda, then you will get k value. Now let us write the definition of eigenvector. The eigenvector definition is this: a into x equal to lambda times x. This A is matrix. So 4, 1, 2, k 2, 1, 14 minus 4, 10 into this x is eigenvector 1, 2, 3 equal to lambda into 1, 2, 3. Basically I want k. K is available in the second row, so expand second row only. So k into 1 k plus 2 into 2 4 plus 1 into 3 equal to expand second row. This is 2 lambda. This implies k equal to 2 lambda minus 7. 2 lambda minus 7. So once you get lambda, then only you can get the value of k. But in the first row all elements are given. In the last row all elements are given. So by using either first row or by using either third row, you can easily get the value of lambda. You can use any row. So whatever the row you apply, you must get the same value of lambda. If you are getting 1 lambda by expanding first row, or if you are getting different lambda by expanding third row, in that case this is not a correct eigenvector. So if something is an eigenvector, you can expand any row, you will get the common value for that lambda. Now expand first row. So this is 4 plus 4 into 1 plus 1 into 2 plus 2 into 3, 6 equal to lambda. So this implies lambda equal to 12. Now we got lambda, replace lambda value here. So k equal to, this is 2 lambda minus 7. So this is 24 minus 7. So k value is 17. Note this. Next we move to question number 59. consider the matrix A equal to, consider the matrix A equal to 50, 70, 70, 80, whose eigenvectors corresponding to lambda 1 comma lambda 2 are given by x1 and x2. So with respect to lambda 1, the eigenvector x1 is given by this. This is 70, lambda 1 minus 50. And with respect to second eigenvalue lambda 2, the corresponding eigenvector is x2, that is given by lambda 2 minus 80, 70. So we need to find x1 transpose into x2. We need to find out this. Now this is my matrix 50, 70, 70, 80. It's a 2 by 2 matrix. So two eigenvalues are given. They are not given values, but notations are lambda 1, lambda 2. With respect to lambda 1, this is my eigenvector x1. With respect to lambda 2, the eigenvector is x2. And they were expecting x1 transpose into x2. If you want to calculate x1 transpose, you must know lambda 1 generally. Because inside x1, lambda 1 is required. Inside x2, lambda 2 is available. But this is not a simple matrix to find its eigenvalues. Is there any shortcut possible in this? Sum of rows or sum of columns? Certainly not. So but this is not an upper triangular matrix, not a lower triangular matrix. Therefore, but everything is multiple of 10. So you can take 10 common. So in that case, you will get 5, 7, 7, 8. It's a real symmetric matrix. Eigenvalues will be real. But even by that also, you will not get lambda 1, lambda 2 values. You will get some different real numbers. So let us do not waste time to evaluate lambda 1, lambda 2. At first, let us try to simplify this x1 transpose into x2. So here x1 transpose into x2. This is x1 transpose of this 70, lambda 1 minus 50 into x2 is this lambda 2 minus 80 and this is 70. And in this case, the size of this matrix is 1 by 2 and this is 2 by 1. So this 2 and this 2 will be eliminated. The result is 1 by 1. So when you multiply this, when you multiply these two matrices, the resultant matrix will be size 1 by 1. So 1 by 1 means only single element. So therefore multiply 70 with this. So this with this. So 70 into lambda 2 minus 50. 70 into lambda 2 minus 80 plus lambda 1 minus 50 into 70. So this implies 70 into lambda 2 minus 5600 plus 70 into lambda 1 minus 3500. So you can take 70 common. 70 into lambda 2 plus lambda 1 minus 5600 minus 3500, 9100. Now this is 70 into, this is what? Sum of eigenvalues of this matrix. Sum of eigenvalues is a trace. Sum of eigenvalues is a trace. So lambda 1 plus lambda 2 equal to sum of these two. Sum of these two is 130. So 70 into 130 minus 9100. This is 9100. So the answer is 0. So in that we have applied only one result, that is sum of eigenvalues equal to trace. I think you can understand the importance of the first shortcut. In almost in all problems, in 90% of the cases, we were using the property sum of eigenvalues equal to trace. Even mostly in almost in all questions, we were using product of eigenvalues equal to det. So by looking at the all previous GATE questions or IES questions, this is very clear to all of you that sum of all eigenvalues is a trace product of eigenvalues equal to det. Not this. Right, we were closing this session. Thank you so much. In the next session, we start the questions from 60 to 63. That is again questions will be on eigenvectors. After that, we start new concept, Hamilton theorem, spectral theorem, followed by system of linear equations. Thank you so much.